All right, so we're moving into chapter 5, which is getting into the good stuff. And so hopefully this can be valuable, and I'll have to kind of go through it kind of quick because, you know, we lost 10 minutes because of computer. So chapters 5 and 6 are about random variables, okay? And so in chapter 5, we're going to discuss what are called discrete random variables. And then in chapter 6, we'll talk about continuous random variables. So a random variable is, all it is a numerical description of the outcome of an experiment, right? So if we run 50 trials and we record our 50 outcomes, we would call those random variables, okay? And so this chapter focuses on discrete random variables where we assume there's a finite number of values. That's a really terrible. Don't look at that. I should have looked at that more closely before I added their slide. All we mean with discrete random variables is that the numbers we're dealing with, I'm sure some mathematician would fight me on this or something, but all it means is the numbers we're dealing with are all in whole numbers, okay? No decimal places in between them. So this would only deal with experiments where the output is in whole numbers. Like if we're saying, what's the number of people who use the computer lab? And then we track each day how many people do, right? We never have like 12.2 people unless we do an average. But our actual count is just going to be in whole numbers, no decimals. So don't worry about that. That's confusing. It will make more sense when we start to work with continuous random variables, because if I say, you know, the smallest day was we had 20 people use the lab, and the biggest day was we had 100 people use the lab, I could say there's a range between 20 and 80, and it's this sort of finite space, right? So there's really, 20 and 100, so an 80-point range. But it's a finite space in that there's really only so many points between 20 and 100, 80 points, and that's it. Whereas if we were doing continuous random variables, which allows for decimal places, now we could have 20 or 21 or 22 or 23, but we could also have 20.1, 20.01, 20.001. And so when we get to continuous random variables, our sample space becomes infinite, in that there is, in essence, an infinite number of potential decimals between 20 and 100. So that's what that means, but it's kind of confusing. So I want you to think right now, as we get into these numbers, be thinking this is only whole numbers, no decimals involved in the actual data, okay? So again, we kind of saw this before, but random variables, you know, we would say, well, what are the random variables for a coin flip? Well, it's either a heads or a tails. If we wanted to assign it a numerical value, it could be 1 and 0, right? It could also be 1 and 2. I mean, we could assign it whatever numerical value we want. Roll of a die, 1, 2, 3, 4, 5, 6. Number of customers who place an order. If there's 5 customers, could be 0, 1, 2, 3, 4, 5, etc. Okay, so these are what we mean when we use the term random variables. All right, so discrete probability distribution, like I said, has these numbers, but they're only whole numbers. So this one is using past data on daily car sales for 300 days. DeCarlo Motors puts together this sort of tabular summary. If you think about it, all this is a frequency distribution, right? So there were 54 days where they didn't sell any cars, and then there were 117 days where they sold 1 car, etc. Okay, so this would be like our data set, and we could look at that and see how that's distributed, and I'll show you that in a minute. We know that if we take, you know, the probability, so they're showing this as a function of x, and all that means is the probability. So the function, if the function is the number of days divided by the total number of days, then f of x would be the number of days divided by the total. So 0.18, 0.39, 0.24, etc. So I guess what we're really getting at here is we've already kind of started into this sort of thinking, but now they're trying to show you more in mathematical terms, right? And so when you see f of x, it's like scary because it's like, oh, what does it mean? All it means is that's the equation, okay? So I don't know how well you can see that with glare and stuff, but this would be if we graphed that probability distribution. More often than these bars, when you see these, you'll see them just done as like lines. So again, this is not really any different than like a frequency distribution, right? Or a frequency chart, just that instead of having them all together, it has just lines. All right. So one thing we have to learn how to calculate is what's called the expected value of, and all the expected value is the weighted mean of a function. So again, this looks all crazy, and I just want to show you the math, but then say, don't worry too much about it. So the expected value is the same as the weighted mean of the function. So the sum of xf of x, okay? But don't worry, because we have our friend Excel, okay? So if we wanted to find the mean of this probability distribution, we can just use this. That's for standard deviation. We do sum product of A2 to A7. So before, when we did this, we would do this times this, this times this, this times this, this times this. It's like a weighted average, right? And then we would add them all up at the bottom. So they're just showing you can use a new function called sum product, which means if I do A2 to A7, B2 to B7, that's telling it take the sum of that times that, plus that times that, etc. Okay, so that's sum product. That's a good one to practice using because it's a pretty valuable function. So all the mean is the weighted mean of the probability distribution, which would be the quantity times the sum of the quantity times the probabilities. Okay, again, we've already done weighted mean, so this isn't brand new. Sometimes that mean is also called the expected value. Okay, so if we have 18% of our days had sales of 0, 39% of our days had sales of 1, 24% had sales of 2. Okay, when we run that, we come out with a mean of 1.5. What that means is, based on the probabilities together with the quantity of sales, we expect the average day we're going to sell 1.5 cars. We know we can't sell 1.5 cars. So it's somewhere between 1 and 2 cars is what we're saying. So that's all expected value means, okay? Is the weighted mean of the probability distribution. The variance, again, we can use sum product, do the deviation of the mean, and then the standard deviation is the square root of the variance. We have to know how to do this. We can't just use variance and standard deviation because these are weighted. Remember when you did the weighted means, if you just have a data set, fine. But when you have it presented to you as a weighted mean situation, or in this case, what's called a probability table, we have to do the math. And so knowing how to do this will become important, okay? All right. So all of you taking accounting or are taking accounting? So you remember when you first started accounting, the hardest thing about accounting was not the math part of it. That was doable. It was the whole like putting things into the right categories. Like, wait, is this an asset? And then assets increase with a debit. Oh, this is a liability. How is it? Like, that's the hardest part, I think. Harder than like any of the math in it. So the same thing's going to happen with these distributions. Okay, I'm going to show you like four or 5 different types of distributions. And the most important part of what I'm going to show you will be your ability to look at a problem and recognize I'm dealing with this type of distribution, because that will determine how you go about solving it. So if there's like, and like I said, right now we're doing all of these discrete random variables, and then next chapter we'll do continuous random variables. So for this whole unit, when we get to the next test, being successful will depend upon you being able to go, A, am I dealing with a discrete or a continuous distribution? B, if I'm dealing with discrete, am I dealing with which type of discrete distribution? Okay, so that's what I want you to focus your energy on as you go through the homework, is being able to identify the difference between the two. I'm just giving that as a preamble now, but it won't make sense until you're actually working with the homework, or it won't make as much sense. All right, so the first type of distributions we have are called bivariate distributions, and that means two variables. Bivariate, right? Doesn't mean it's a distribution that goes both ways. Maybe it does, has two variables, right? All right. So each outcome of a bivariate experiment consists of two values, one for each random variable. For example, rolling a pair of dice, right? So now we could have 1 and 1, we could have 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, 2 and 1, 2 and 2, etc. Right? There's two variables. Unless someone said, well, what's the total amount you get from rolling two dice? Then that'll be one variable. You could get 2, 2 1 is 3, etc. So when dealing with bivariate probability distributions, we're often interested in the relationship between the two variables. Think of some of your presentations you did. In fact, even though we hadn't really got to this sort of thing very much yet, some of you were kind of eager to be like, I want to understand the relationship between this. I'm trying to remember who did one where they went ahead and did like a coefficient of a correlation coefficient anyway. Which one of you did a correlation on your presentation? I guess we don't remember. All right. Or you're not listening, one of the two. But like, we get to, it's an interesting thing, right? If I say, hey, what's the age of students and like their age when they start college and their first semester GPA? And then we would ask ourselves, is there a correlation? Like, do older students do better? Do younger students do better? Is there sort of a curvilinear relationship where older is good until you reach a certain point of older and then it starts to taper down again or something like that, right? We want to understand the relationship between the two variables. If you think about it from a statistical standpoint, this is sort of the ultimate goal, is we want to try to understand which inputs, which things I can do to make the outputs most desirable. What marketing can I do to increase my sales the most? What employee benefits can I offer to get me the strongest and best employees, right? Whatever. That's what we're hoping for ultimately with business statistics, is like, how do we manipulate the system to get the best outcomes? That's really what we're looking for. So that's bivariate. You'll recognize bivariate because there'll be two variables. That's easy in one sense, where they're being compared to each other. All right. The second type of probability distribution, discrete probability distribution, is called a binomial probability distribution. So these are fairly easy to recognize because the outcomes are always limited to two possible outcomes for each data point. They either can be a success or a failure. That's it. So in business, we might say, let's say there, did we make a sale today or did we not make a sale? Or is this product coming off the production line faulty or is it not faulty, right? So with binomial distributions, look for something that is like either or. It's either a success or a failure. Yeah, I guess success or failure is the best way to describe it. So the probability of success, we denotate with a P for probability, and the probability of failure is 1 minus P. In other words, the probability of success plus the probability of failure have to equal 1. In other words, those are the only two options. We succeed or we fail. Okay. And all of our trials are independent. That means, so think of a coin toss. That's a perfect example of a binomial probability distribution. I get a heads or a tails. So that's all I can get. We're going to discount landing on the edge, even though in theory it's possible. Okay. Heads or tails. The second time I flip, so let me ask you this. If I flip 5 heads in a row, on the 6th flip, what's the probability of me getting heads again? It's not low. It's 50%. But I think you're right, because for me, like naturally, I would think there's no way that's happening again, right? but it truly is independent. It is not related to the previous outcomes. I mean, unless I have a trick coin or something, but again, we're speaking generally here in normal terms. So I mean, that's why we use things like coin flips in sports, because they're meant to be truly random every time. So the trials have to be independent, even if our natural inclination is to be like 10 in a row. That can't happen. What's interesting is if you flip 10 coins in a row, you'll often get like a 70-30 split or a 60-40 split, or sometimes even like an 80-20, right? It starts, but that, think about how like getting a 5 and 5 split, if you did it, 10 times and then did it 10 times more and 10 times more and 10 times more, you could graph that and you'd be like, most of the time I get a 5 and 5 split. Sometimes I get a 4 and 6 split or a 6 and 4 split. And so it's going to end up looking over like, say, thousands of trials, it's going to look like this. Okay. Where your mean, which is going to be a 5-5, and then 6 and 4, 4 and 6, etc. Down to on some rare occasion, when you flip 10 in a row and somehow got like all 10 of them be heads, that would be like, that would barely ever happen. Okay. And so what we notice is with all of these distributions, as the n increases, the n meaning the sample size, they tend toward a normal distribution every time. It's kind of a crazy thing. Like there's certain things in the universe that denote to me that there's some sort of power working beyond just randomness. The fact that almost all distributions with large sample sizes tend to that shape. It's weird. You know what other one always gets me? I learned about it like in a physics class. Like most things, their solid form is more dense than their liquid form. So like solid will sink in a liquid, but water is different from that. And water is the basis of our life in essence. And so could you imagine if ice were more dense than water, lakes would freeze from the bottom up and kill all the animals. But instead we have a sheet of ice floating on top and the animals can still live underneath. It's mind-boggling to me. Because if I had steel and I threw solid steel into molten steel, it would sink. It's more dense. It's interesting. Okay, we need to go there. This is probably why my kids all chosen sciences, right? Because I'm always like, have you ever thought of this? And they're just like, whoa, that's weird. And then they grow up and then they're calling me, Dad, did you know this? I did not know that. My kids are all smarter than me. My daughter has a master's in chemistry and she's always like calling me with something. And I'm just like, I did not know that because I don't study it to the level of a child. All right. So there's our binomial probability distribution. Our interest in the number of successes occurring in n trials. So if we let x denote the number of successes occurring in n trials, then this would be our function. The function of x is n exclamation point. Remember what that means? You guys remember what that means? The number times one less, times one less, times one less, all the way down, factorial, right? Times x factorial times n minus x factorial times p to the x as 1 minus p, that's the probability, to the x, as 1 minus p n to the x. Woo! Now, it looks like a big scary formula, but I bet you, if we had to, we could create an Excel calculator. We would just put our variables. We'd have an n, an x, a p, and that's it, actually, right? And then we could be like, we could just put parentheses and be like n factorial divided by parentheses x. In other words, we could build a little calculator that would do that. And then all we'd have to do is change our n, our p, and our x, and it would work, okay? So it's not as hard as it sounds once you sort of like break it down piece by piece. But the good news is that there is an Excel function called binom.dist for binomial distribution equals binom.dist, which I'll show you. So here's an example. Martin Clothing Store wants to determine the purchase decisions of the next 3 customers who enter the clothing store. On the basis of past experience, the store manager estimates the probability that any one customer will make a purchase is 0.3. Okay, so what's the probability that 2 of the next 3 customers will make a purchase? So another way of looking at binomial distributions is this decision tree like we had in the previous chapter, right? So these are independent of each other. It's not like if one customer comes in and makes a purchase, it's more likely that the next one will or won't. It's still going to be 30% chance for each customer. So we have success on the first one, then the second one can either be a success or a failure, and then the third one. So those are our potential outcomes. Again, you won't really need to know how to do that. I'm just trying to show you, if you're a graphical learner, that's what it looks like. Okay, I'm not a graphical learner. Those things don't help me. But I'm married to one, so everything she sees is in pictures. And I'm like, just give me data, baby. All right, but we'll use this function, which is equals binom.dist, and then we'll use the number of trials and the probability, and then where is it? B2, so B5. So there's our value of X, then the number of trials, then the probability, and then false. Just always use false on it. Okay, we can talk another time about what true means, but and then what it does is it returns us the probability. And guess what? If we add all those up, we're going to add up to 1. Because people are we're either going to have 0 purchases out of the next 3 customers, or 1 purchase out of the next 3 customers, or 2 or 3. That's it, right? So just remember, so you'll notice in the output here, there's more than 2 options, success or failure. The output, we're saying, what's the percentage of these many? It was the input that helped us define it. In the input, it was either a success, they purchased, or a failure, they didn't. Okay, so that's binomial distributions or binomial probabilities. All right, here's just some things that we can't use Excel to calculate for us, unfortunately. So we'll have to figure out how to use these scary formulas. But, and again, these formulas will be in your book too, so you can write them down in your notes or know that they're also there available for you. But certainly when you take the exam, you'll want to have them in your notes, right? So the expected value is just n times p. Remember that n is the number of trials, p is the probability, okay? The variance is np times 1 minus p. So again, that's not super hard math. And then the standard deviation is just the square root of the variance. Remember, so this little guy here, this sigma, that means standard deviation. And you'll notice that variance is always recorded as standard deviation squared. So if you have variance, always all you have to do to find the standard deviation is take the square root of it. Okay. So that's binomial distributions. Brooke, are you ready for me to move forward? I notice you're taking some notes. Okay. So here's the Martin clothing one we just looked at. The expected value is 0.9. So out of 3 customers, based on a 30% chance of any one customer being a success, we would expect out of 3 customers on average, we'd have 0.9 successes, which really means somewhere between 3 and 4 customers, every 3 and 4 customers, we're going to make a sale, is what that's telling us. Okay. Our variance is 0.63 and our standard deviation is 0.79. Okay. All right. The second type of probability, or the third type of probability distribution that we might deal with, and these are discrete, meaning the inputs, the variables at the beginning aren't in decimals. Okay. It's called a Poisson probability distribution. It's like Poisson. It's French. I don't know how to actually pronounce it. That's probably pretty close, but not Poisson. That means fish. Like les poissons, les poissons. How I look? Okay, it's my movie. Sing with me, people. It's Little Mermaid. Anyway, nobody wants to sing. So Poisson probability distributions, random variable that we use most of the time, and really for this class, only use for estimating the number of occurrences over a specified interval of time or space, but usually time, okay? So things like how many people are going to come through the stall or through the turnstile at a subway in a given hour, right? How do we estimate that? Again, we would have to like measure. So if you think about it, it's always in reference of like people per hour, or you know, sales per minute, or something like that. Okay, so it's almost always over a space of time, or sometimes over a space. Like, you know, how many pounds of cotton yield will we get per acre? Okay, but so when we're looking for these, it's always something per something. That's one clue that you're dealing with a Poisson distribution. Okay. All right, there's a number of knot holes in 14 linear feet of pine board. I don't know. Maybe if you're in the lumber business, that matters, right? Number of vehicles arriving at a toll booth per hour, number of leaks per 100 miles of pipeline. I thought it'd be 0. I don't know. I don't know much about pipelines. I didn't know they had, like, leaking was normal, unless the Russian government's involved. Okay, they blew up their own pipeline or whatever. So Bell Labs used Poisson distribution to model the arrival of phone calls. So they knew how big to build. This is back in the early days of phones, right? How big of a network they needed to create to actually handle traffic and volume. So you think about that. If that's the business you're in, and now you're going to offer phone service to an area that previously hasn't had it, how do you know how big and robust to build it? Except maybe you say, well, we built these in other places, and on average, this many households, you know, signed up or whatever. That could help. All right. Again, I sometimes I feel like these things they give you are more confusing than they are helpful. Except maybe number 2 is important to consider: the occurrence or non-occurrence of in any interval is independent of the occurrence or non-occurrence in any other interval. So again, all we're saying is success or failure, occurrence or non-occurrence within the interval is independent. Okay, so that you know, if 10 people come through per hour, that has no bearing on the next hour, or within that, if I have 10 people come through, that has no bearing on if an 11th is going to come through or not. Those are independent of each other. Okay, that's what we're kind of saying. So the Poisson distribution looks like this. So the mean number of occurrences to the power of the number of occurrences times E, which is a constant. Again, if this were a math class, we'd probably look up who first proved E. I don't care. I just give me the number and I'll use it. Okay. To the negative mean number of occurrences divided by X factorial. Okay. Again, if we had to create a little calculator to do that, we could do that. Luckily, the creators of Excel created a calculator for us, so we don't have to do that. Okay. So here's an example: arrivals at the emergency room. The average number of patients arriving in an emergency room in a large hospital in a 15-minute period of time on weekday mornings is 10. 10 per 15 minutes. Whew. All right. What is the probability then of 5 arrivals in a 15-minute period of time on a weekday morning? So again, your first order of business is to be like, what type of distribution am I dealing with? Does this appear to be bivariate? No. There's not 2 different variables. There's just one to deal with. Is it binomial, success or failure? Well, maybe they arrived or didn't arrive, so it gets confusing, right? But in this case, when it says in a period of 15-minute period of time, when it's saying this per an amount of time, that's your clue you're dealing with Poisson. Okay. So we could calculate the f of x. So for 5, f of 5 is 10 to the 5 times the constant to the negative 10 over 5, 0.378. Or we can use the function equals Poisson dist, and then we put in the number of arrivals, and then the average number of occurrences, and false. And here what they did is they did it for all possible versions of it. Usually in your assignments, you'll just say, what's the probability of this one thing? And you can just do that. You don't have to solve it for all possible values. Okay, so that's a Poisson distribution. An interesting property of the Poisson distribution is that the mean and variance are equal. And therefore, if we know the mean, then we know the variance. And if we know the variance, we just take the square root of it, we can find the standard deviation of that distribution. Okay. All right. Hypergeometric. Don't you love the names of these? So we have bivariate, binomial, Poisson, and now hypergeometric probability distributions. So they are closely related to binomial distributions, but the trials are not independent. And the probability of success changes from trial to trial because they're not independent. Okay. So here's what their function looks like. So here's an example. Electric fuses produced by Ontario Electric are packaged in boxes of 12 each. Suppose an inspector randomly selects 3 of the 12 fuses in a box for testing. If the box contains 5 defective fuses, what is the probability that the inspector will find exactly 1 of 3 fuses defective? Okay, so that seems a little scary, looking at that as a word problem, but recognize, so what makes this not independent, or what makes this dependent? Because this is what we'd have to do to recognize this as hypergeometric. Anybody have a guess? So in the earlier binomial probability distributions, the flip of the coin as an example, what I got on one heads has no effect on what I get on the next one. But in this case, I have 12 fuses in a box, and I pull out 3. 1, 2, 3. Okay. So if I pull out a defective, now the number of defective fuses in the box is different for the second pull. Does that make sense? Or if I pull out a non-defective, in other words, by pulling out of a box of something, I'm reducing the quantity that are in the box. And so each time I make a change to it, then I'm changing the probability. Does that make sense? That's what dependency means in a statistical sense. Okay. It's not like, you know, it lives in your basement until it's 30 and then still is on your car insurance till it's 40, right? That's a different form of dependency. No offense to anybody who's living in their parents' basement. It's smart. Do it now while you can. Right? You live in your parents' basement. They don't have a basement. It's sorry. Dependency jokes. Hilarious. All right. So here's Ontario Electric. We have X equals 1, the number of defective fuses selected. N is the number of fuses selected. Big N is the total number of fuses. And R is the total number of defective fuses in total. So anytime we're dealing with one of these, in essence, these are the 4 variables we'll need. So what we're saying is there were 12 total. I pulled out 3. Of the 12, 5 were defective. And of the 3 I pulled out, 1 was defective. So now I can solve all that and say, what was the probability of that? 0.4773. Okay. There's our mean, which is just n times r over n. Our variance, which is a little bit beefier, n times r over n times 1 minus r over n times big N minus little n over n minus 1. Again, that looks like a lot, but it'd be pretty easy to create a little calculator in Excel. And then we use Excel. It's just called, oh, that says Poisson. Sorry, that should be hypergeometric. It's equals hypgeom.dist. And again, if you know those 4 variables, the total number, the number within the total that are defective, the number that you're pulling out, then you can solve, and the number that of the ones that you pulled out that was defective, you can solve for the probability of any given one of those. Okay. All right, so that's it for this chapter. It's pretty doable, but like I said, what I want you to focus on is sort of differentiating and getting good at that. Because you know how things are. At first, you're like, oh, I don't know, there's just all this information. But the more you do it, the more you're like, okay, I can see the differences between these 4 things, and know which which Excel function to apply, and know that when I know it's this, what variables I'll need to actually punch into the Excel problem. Does that make sense? That's more important to me than the math. Because again, I'm giving you a page of notes. You could write down the formula, and if you had to do a formula, you could do it. This is still not as hard as some math you've done if you've taken calc or elements of calc or even trig or whatever. Trig's the worst. All right, that's all I have for you today. Just think, if I hadn't had computer problems, we got out 13 minutes early. Sorry. Have a good day.